Hello everyone. So in this lesson, we'll be learning about two waves that are in phase and out of phase. Okay, let's look at this wave and let's consider 2 points on this wave, the two red dots and the two blue dots. So when the wave moves, from left to right, you see that the two red dots are in phase with one another, whereas the red dot and the blue dot are out of phase. What it means is when the red dot is going down, the blue dot is going up and vice versa. So we can see that the two red dots are in phase. When one goes down, the other goes down together. And the blue dot and the red dot are out of phase. Okay, 1 lambda is defined as the distance between two adjacent points that are in phase with one another. Right? 2 lambda will be the distance between two adjacent dots, all right? Between here and here are adjacent dots, and between here and here are adjacent dots. So this is also defined as 1 lambda. So the 2 lambda will be the distance between this red dot and this red dot. Okay, between 2 points, the red and the blue dot, this represents 0.5 lambda. So lambda is the wavelength of the wave. And the distance between the first red dot and the second blue dot represents 1.5 lambda. So between the blue dot and the red dot, they are out of phase with one another. Okay, let's try this example, right? So in this diagram, we see two waves, right? One blue and one red. So the question is, are these two waves monochromatic? So the answer is yes, they are, because they have the same frequency. So we can see, right, that the frequency of the wave or both wave is actually 50 Hertz. And how do we find the frequency? We find it from the period of the wave. So the period of the wave will be the time taken for the wave to make one complete oscillation. And in this case, we can see the blue wave takes 20 milliseconds to make one complete oscillation. The same case as the red wave, right? From here to maximum again is 20 milliseconds. So monochromatic light are basically light that consists of a single frequency. Okay, the next thing is, what's the phase difference between these two waves? So basically, all right, by how much I have to shift the red wave so that the crest of this wave coincides with the crest of the blue wave. So by how much I have to shift it, that is known as a phase difference. So from here, we can see that the phase difference is actually a quarter of a lambda, or 0.25 lambda. So in other words, if I want the two crests of the two waves to coincide with one another, I have to shift the red wave by a quarter of a lambda, which you can see, right? By shifting it a quarter of a lambda, half a quarter of a wavelength, then the two crests will coincide with one another. Okay, in this case, what's the phase difference between the blue wave and the red wave? So by how much I have to shift the red wave so that the crest of the red wave coincides with the crest of the blue wave. So you can see that I have to shift it by 0.5 lambda. Okay, let's take for instance, if I have a source. So this is the wave created by source 1, which is represented by a sine wave. And let's consider source 2, right? Which is also a different light source and is also a sine wave. And we can see that these two waves are in phase with one another, which means when S1 is a crest S2 is also a crest. And when S1 is a throw, S1 is also a throw. So the phase difference between them is 0. Okay, now if I subdivide the wave, right, of S2 into 10 different segments, right, of equal length. Right, you see this is 10 equal segments for 1 lambda. So what happens if I shift S1 by 1 segment? So what's the phase difference now between S1 and S2? You see that they are now out of phase. They are no longer in phase because the crest from S1 doesn't coincide with the crest from S2. So in this case, since I've shifted this wave, right, by 0.1 lambda, the phase shift between them would be 0.1 lambda. If I shift the wave by 2 segments, then the phase difference between them will be 0.2 lambda. And this will be 0.3 lambda, 0.4 lambda, 0.5 lambda. All right, so they are phase shifted by 0.5 lambda, 0.6, 0.7, 0.8, 0.9, and 1 lambda. So once the phase shift is by 1 lambda, they are in phase again because a crest from S1 coincides with a crest from S2. All right, so our outcome describe what is meant by two sources being in phase and out of phase. Okay, next describe coherent wave sources are wave sources that maintains a constant phase relationship with each other, and explain why light from an incandescent light source is neither coherent nor monochromatic. Okay, what is coherent? And what's the difference between coherent and monochromatic? So monochromatic, like what I have defined earlier, means light of a single frequency or light of a single lambda. So what is coherent? Okay, coherent is basically, right, waves, right? So have you all seen soldiers marching, right? So let's take, for instance, the soldier first in line takes out his right leg. The soldier last in line also takes out his right leg. So after they march for, let's say, 1 kilometer, right, the first soldier takes out his right leg. The last soldier in line also takes out his right leg. So in other words, they are coherent because they maintain a constant phase relationship. Right? So a good example of coherent waves are basically soldiers marching. So the question is, why wouldn't an incandescent light source emit light that is monochromatic? So an incandescent light source is not coherent, neither is it monochromatic. Okay, if you light up a light bulb and you view this light bulb through a prism, you find that the prism will break light into its components of colors, right? From red, orange, yellow, green, blue, indigo, and violet. So this is what makes up white light. So since the light here consists of different colors, different frequencies, that means the light source is not monochromatic. So if the light source is not monochromatic, then it cannot be coherent. Okay, so remember just now for coherent, it's like soldiers marching. So when the first soldier takes out his right leg, the last soldier in line must also take out his right leg. And when they march, let's say for a 1 kilometer distance, when the first soldier takes out his right leg, the last soldier in line must also take out his right leg. So they maintain a constant phase relationship. So for them to be coherent, that means the steps that they make must be the same. So in other words, lambda is actually the same in order for the light source to be coherent. So since an incandescent light source emits a continuous range of frequencies from low frequency red to high frequency violet, you find that the light source will not be monochromatic. So if it's not monochromatic, it is not coherent. So the question is, why is light that's emitted from an incandescent light source not monochromatic? And the reason can be explained by how light is produced. You see, when current flows through the filament, right, the electrons are going to vibrate. And when the electrons that are charged particle vibrates, they generate electromagnetic radiation. So some electrons vibrate at a very high frequency because of the high temperature. So they are going to emit high frequency electromagnetic radiation. However, there are some electrons that vibrate at low frequency. So they are going to emit low frequency electromagnetic radiation. So that's why an incandescent light source is emitting light that is not monochromatic. All right, so clear about coherent, clear about monochromatic. Okay, next, when two or more electromagnetic waves overlap, the resultant electric and magnetic fields at a point can be determined by using the principle of superposition. Okay, superposition is basically adding up two vectors. So if I have two waves, there'll be two different electric fields from the two waves. So to find the resultant of the two waves, I add up the electric field, which is a vector quantity. And I similarly add up the magnetic field of the two waves, right? So when the waves at a point are in phase, then constructive interference occurs. When the wave at a point is out of phase, then disruptive interference occurs. So using the principle of superposition to describe and represent constructive and destructive interference. Okay, so let's explain about interference. But before that, let's explain about the path difference. Okay, let's take for instance, right? There are two students, student 1 and student 2. And they decide to meet at a certain point, all right, at point A. So student 1 walked 50 meters, whereas student 2 walked 20 meters to meet each other at point A. So when I say path difference will be who walked longer. We can see that student 1 walked longer as compared to student 2. And how much longer? So how much longer will be the path difference, which is 50 meters minus 20 meters. So let's take, for instance, they decided to meet at a different point instead at point B. So student 1 walked 15 meters to reach point B, whereas student 2 walked 60 meters to meet point B. So what's the path difference? So the path difference now will be the longer S2B minus S1B. So the path difference is 45 meters. So whenever I ask, the question asked about path difference, is basically two light sources, S1 and S2. We are trying to find out which light source travel further to reach a certain point in space. All right? So the path difference will be the larger minus the smaller. Okay, so let's look at this. There are two light sources, right? Both of them are emitting light sources in the form of sine wave. So these two waves, right, are in phase with one another. So what happens is, if S1 starts slightly ahead compared to S2, so how much earlier did it start, right? It started 0.1 lambda ahead. So 0.1 lambda is known as my path difference. So the 0.1 lambda path difference causes the two waves to have a phase shift of 0.1 lambda. So now S2 started 0.2 lambda ahead from S1. So we say that the path difference between S1 and S2 is 0.2 lambda. You see, it started 0.2 lambda. So it has to travel 0.2 lambda before S1 starts. So the path difference is 0.2 lambda. So this 0.2 lambda will cause a phase shift of 0.2 lambda between S1 and S2. The same case S3, S4, S5. So now, right, we can see that S2 has started 0.5 lambda ahead compared to S1. And the phase shift between them is half a lambda. That is when S1 is a crest, S2 is a trough. And this is 0.6 lambda path difference, 0.7 lambda, 0.8 lambda, 0.9 lambda, 1 lambda path difference. So now S1 starts 1 lambda ahead from S2. So as the path difference is 1 lambda. But interestingly, right, when the path difference is now 1 lambda, we find that the two waves are now back in phase with one another. You see, this is a crest, and this here is a crest as well. So when S2 is a trough, S2 is again a trough. So when the path difference between the two light sources are 1 lambda, we find that the waves are now in phase with one another. Okay, constructive interference will happen when the crest from one wave will meet up with the crest from a different wave. Okay, electromagnetic wave consists of both electric field and magnetic field. So let me draw, right? This here represents the electric field. So assuming that this electric field is 5 Newton per Coulomb, right? That's the amplitude of the wave. And another wave that also has an amplitude of 5 Newton per Coulomb. So these two waves are in phase with one another. So by using the principle of superposition, what is the resultant of these two waves when they meet up together? So the resultant of this wave would be the crest from S1 add the crest from S2 to give you constructive interference. So this wave is known as a very bright light. So it's known as constructive interference because the amplitude of this wave is basically the vector sum of S1 plus S2. That's what you get as 10. Okay, what happens if the path difference between S1 and S2 now is 1 lambda? Like the example that I gave you just now, if the path difference is 1 lambda, we find that S1 and S2 are still in phase with one another. So if I say, what is the resultant of S1 plus S2? I will still get a peak of 10, all right? Because it's a vector sum of S1 plus S2. So I will still get constructive interference when the path difference between S1 and S2 is 1 lambda. Okay, what happens if the path difference between S1 and S2 is now 2 lambda? Okay, can you see that this is 2 lambda. So S2 starts 2 lambda ahead of S1. So what's the resultant of S1 plus S2? You find that I will still see constructive interference because it's a crest from S2 plus a crest from S1. So in general, right, I will see constructive interference will occur whenever the path difference is 0, 1 lambda, 2 lambda, 3 lambda, 10 lambda, 100 lambda. All right, it's always a whole number lambda. That's when I will see constructive interference. Okay, now let's describe destructive interference. Let's take, for instance, S1 started half a lambda ahead as compared to S1. So the path difference is 0.5 lambda. So if I ask you, what is the resultant of S1 plus S2? That is, S1 is positive 5, the crest, meeting with the throw from S2, negative 5. In this case, the throw from S1 meets up with the crest from S2. So when I find the resultant, I find that the resultant will always be 0. So this resultant that is 0 means destructive interference. That means I don't see any light at all. Okay, let's consider what happens if S1 starts 1.5 lambda ahead from S1. You see, it started by, this is 1.5 lambda. So it started by 1.5 lambda ahead from S1. Again, we can see that the resultant of the two waves will be 0 because it's always a crest from S1 meeting a throw from S2. So in general, we can write destructive interference will occur whenever the path difference is 0.5 lambda, 1.5 lambda, 10.5 lambda, 100.5 lambda, and so on and so forth. So whenever there's a 0.5 lambda path difference, then the two waves will interfere destructively. Okay, so let's reflect back on the outcome. When two or more electromagnetic waves overlap, the resultant electric field and magnetic fields, right, at a point can be determined by using the principle of superposition. That means we add the two electric fields, all right, electric field from S1 plus electric field from S2 using vector, right, adding up as their vector. That's using principle of superposition. So when the two waves are in phase, then you'll see constructive interference. So when I say in phase, that means S1 is a crest, S2 is also a crest. So when a crest meets a crest, you get constructive interference. Out of phase will be when S1 is a crest, S2 is a trough. So they are out of phase. So this will give you destructive interference. Okay, let's consider two light sources. Or basically this can be a ripple tank. Right, in the lab, you have a ripple tank, all right, where you have two plungers plunging into a water bath. So when it plunges, right, it creates ripples of waves that you see here. Okay, what we see here, the solid line represents a crest. So you see this is a crest maximum. So in between two crests represents a trough. Then this is another crest. So you see, right, represented by a sine curve. This is a crest and this is another crest. In between them is actually a trough. So the distance between two crests represents 1 lambda. Okay, let's consider 3 points, point A, point B, and point C. Can you calculate what's the path difference? So remember, path difference will be, you see S1 has to travel to point A, right? S2 is also traveling to point A, and they are going to meet at point A. So who has to travel longer? You can see S2 has to travel longer. So the path difference is how much longer must the light source S2 travel in comparison to the light source S1. So we can calculate, right? S1 takes 1, 2, 3, 4, 5 lambda to reach point A. S2 takes 1, 2, 3, 4, 5, 6, 7, 8, 9 lambda. So S2 has to travel 9 lambda, whereas S1 has to travel 5 lambda. So the path difference will be 9 lambda minus 5 lambda. So the path difference will be 4 lambda. So S2 has to travel 4 lambda longer in comparison to S1. Okay, try to find the path difference for point B and try to find the path difference for point C. Okay, so you do for point B, the path difference is 0 lambda. Because S1 has to take 6.5 lambda. Remember, this is a trough, and this is also a trough. Right, so this is 6 lambda, 7 lambda. So in between them will be 6.5 lambda. So 6.5 lambda minus 6.5 lambda, it is 0. The path difference is actually 0. Okay, for point C, the path difference is 5 lambda. Okay, if you notice something peculiar, right? What would I say at point A? I will see constructive interference because it's a crest from S2 meeting up a crest from S1. So when a crest meets a crest, I'll see constructive interference. Point C, right, is also constructive interference because it's a crest from S1 meeting with a crest from S2. Constructive interference. Point B is also constructive interference because it's a trough from S1 here meeting with a trough from S2. So when a trough meets a trough, you also get constructive interference. So notice, right, constructive interference will always happen when the path difference is always a whole number lambda, or basically an integer lambda. 4 lambda, 0, 5 lambda, 100 lambda, and so on. Okay, now let's consider point P, Q, and R. What's the path difference for point P, point Q, and point R? So pause this video, calculate the path difference, and then start again once you are ready. Okay, so for point P, we calculate S2 has to take 9 lambda, whereas S1 has to take 5.5 lambda. So the path difference will be 9 minus 5.5 is 3.5 lambda. But you see, right, point P is destructive indifference because it's a crest from S2 meeting with a throw from S1. Okay, take note, the solid line represents a crest. So this is a crest. So between two crests, there's a throw. Okay, point Q, what's the path difference? It's again 3.5 lambda. So S1 has to travel 9 lambda, whereas S1 has to travel 5.5 lambda to point Q. So therefore, the path difference will be 3.5 lambda. Okay, point R is 1.5 lambda. Okay, so in this case, S1 has to travel longer in comparison to S2. So how much longer? S1 has to travel 6.5 lambda. S2 has to travel 5 lambda. So the path difference is 1.5 lambda. So point P, Q, and R represents destructive indifference because you can always see a crest meeting a throw, a crest meeting a throw, and a crest meeting a throw. So whenever a crest meets a throw, you get destructive indifference. So whenever the path difference is 3.5 lambda, 1.5 lambda, whatever it is, 0.5 lambda, you'll see destructive interference. So when we generalize it, we can say, okay, the path difference, right, between two waves, whenever it's a whole number lambda, then I will see constructive interference, where m here represents an integer. It can be 0, 1, 2, 3, and so on. On the other hand, for destructive interference, I see a pattern of something 0.5 lambda. So destructive interference will occur when the path difference is m plus half lambda, right? Where m is again an integer. So when m is 0, when the path difference is 0.5 lambda, I'll see destructive interference. When m is 1, the path difference is 1.5 lambda, I'll see destructive interference. Right? So in this case, m is always an integer that starts from 0, 1, 2, 3.